Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the hydration energy. Let's understand this concept. What is hydration energy? It is the energy changes accompanying the process of solvation or dissolution of any ionic compounds lattice. Let me write this thing. Uh, it is the energy changes. It is the energy changes, or we can say it is the energy released. It is the energy released when 1 mole of lattice, 1 mole of lattice of an ionic compound dissolves in water. If we take any another solvent or any other organic solvent, we call it as solvation energy, but in case of water, we call this energy as the hydration energy. So let's understand it very deeply. Let me take an example. I'm taking an example of sodium chloride NaCl solid. When we add water in this, then what's happen? The NaCl dissociates to its ions, that's Na positive and Cl negative. Now, what's actually happening? The Na positive ion and the Cl negative ions are making interactive forces with water. Let me take an example. I have taken an water molecule, that's oxygen. Here sits hydrogen, and here sits hydrogen. That's a lone pair of electron and a lone pair of electron. We all know that the electronegativity of oxygen is very much greater than that of hydrogen, so it will attract the shared pair of electron towards itself, due to which it will acquire a slight negative charge, and hydrogen will acquire a slight positive charge. This is called the charge separation, or we call it polarity, or we call it dipole, which we are going to discuss in very much detail in the next lectures. So here we got a charge separation. We got a delta negative charge on oxygen and a delta positive charge on hydrogen. So now what next gonna happen? Now Na positive has dissociated and Cl negative, a dissociated ion from NaCl. So what's happened? So Na positive and Cl negative will make an attractive forces, or we can say the electrostatic forces, due to the opposite charges, and here the Cl negative and H delta positive will make electrostatic forces with each other. Now when Na positive has formed electrostatic forces of attractions with the delta negative charge of oxygen, then we call that Na positive as Na positive aqueous sign plus. Now Cl negative has also made an electrostatic forces of attraction with delta positive of hydrogen, so we will call Cl negative as Cl negative aqueous sign. So the energy change during this process, I'm writing the energy changes as the energy is released. The energy is released in this process of formation of electrostatic forces of attractions, and that energy released is called hydration energy. So the enthalpy change for the above reaction, or the energy changes for the above reaction, is called hydration energy. Hydration energy. So we need to write energy in the products as is an exothermic reaction, and the amount of energy released is called actually the hydration energy. So I hope you all got the concept of hydration energy. Now let's talk about the further points. The hydration energy of any specific ion is directly proportional to the charge density of that ion. I'm writing that hydration energy of an ion is directly proportional to the charge density of that ion. That is, hydration energy of a specific ion is directly proportional to the charge density. We specify or we represent charge density by a symbol phi. Now, what is phi? What is charge density? The charge density is equal to the charge divided by radius. When we talk about a specific group, we always get an equal charge of all the elements constituting that group. For example, group number 1 of your table acquires plus 1 charge, the group 2 acquires plus 2 charge. In that case, when charge is constant, then the charge density is inversely proportional to the radius of the ion. So in short, hydration energy also becomes inversely proportional to the radius of that ion. Now, in the topic of lattice energy, I hope you have watched the previous lectures of lattice energy. There I have told you that lattice energy, in case of lattice energy, it's a formation of lattice. So lattice energy will be inversely proportional to the sum of the cation, the sum of radius of cation and the radius of anion. As it's the formation of lattice, so we have taken the sum of radius of cation and the radius of anion. But very importantly, in case of hydration energy, please pay attention. In case of hydration energy, it is the process of breakage of lattice. So in case of hydration energy is inversely proportional to the radius of cation plus radius of anion. So these two things are very different. Please don't get confused. Now, we will going to discuss in detail about this point. The hydration energy inversely proportional to the radius of cation plus radius of anion. Now, hydration energy. Now let's discuss hydration energy according to a group. Let's take an example of group number 1 of periodic table. The group number 1 is lithium, sodium, potassium, rubidium, cesium and francium. We all know that the group number 1 elements always acquires plus 1 charge. So here the charge is constant, but down the group what is happening? Down the group, radius is increasing. Radius is increasing. Then what's gonna happen? As the radius increase, the charge density will decrease. Just pay attention. I have taken the charge density. The charge density is inversely proportional to the radius of cation in this case. As I saw, the group number 1 is of cations. Now down the group, the radius of cation increases. It increases. So due to which what will happen? Down the group, charge density will decrease. Now, as we know, hydration energy is also inversely proportional to the radius of cation. As hydration energy is directly proportional to charge density, that means as we move down the group, the radius of cation increase, then obviously hydration energy will also decrease down the group. But on the other hand, what we have done in the previous lecture about the lattice energy is also inversely proportional to the radius of cation. If we are talking about only cation, then again in this case also, as we move down the group, the radius of cation will increase, due to which lattice energy will also decrease. So it signifies that hydration energy and lattice energy both will decrease down the group. Both will decrease down the group, but but not in same manner. But not in same manner. For example, if there is more decrease of hydration energy down the group, then there will be a less decrease of lattice energy down the group. Vice versa, if there is more decrease in lattice energy down the group, then there will be less decrease in hydration energy down the group. I'm going to discuss about this thing in detail in the very next lecture of solubilities of ionic compound in group number 2. I'm going to make this video in my very next lecture videos on this topic in very much detail. Just pay attention. So in the next video about the solubilities, I'm going to discuss about this concept and this concept in very much details, and will find out the solubilities of ionic compounds of group number 2 specifically. Now what next? Now let's talk about the group number 17 also, that's of anions. Let me take an example. It's a fluorine, chlorine, bromine, iodine and histidine. As we all know, the group number 17 acquires -1 charge. F -1, Cl -1, Br -1, I -1 and astatine -1. Now again, what will happen? Down the group, comma, radius will increase, and hence charge density and hydration energy will decrease down the group. Now let's discuss it about across the period. Now let's discuss about the hydration energy across the period. As we know, across the period, size always decrease, whereas magnitude of charge will increase. Let me take an example. That's Na plus 1, then Mg2 positive, then Al3 positive. As we are moving across a period from left to right, the charge is increasing. That's a divide by radius. The radius is decreasing, thereby it confirms that charge density will increase. So what's gonna happen? Left to right, charge density will increase, and hence hydration energy will increase. Now we have studied about the different concepts of the hydration energy. Now I'm going to correlate hydration energy with the solubility. I'm writing hydration energy and solubility. Now If the energy released is more when an ionic compound dissolves in any solvent, we are taking specifically water, dissolves in water. It means hydration energy is greater, which signifies that ions tends to get solubilized in that solvent very much quickly. So that means solubility will be very much high of that ionic compound. Solubility will be very much high. It is a direct relationship. That is, hydration energy is directly proportional to solubility. If the magnitude of hydration energy is greater, that means more that solubility of that compound. More is the solubility of that ionic compound in the water. So now let's take some examples. I'm taking it in a quational form. We are having two ionic compounds, the NaCl and the MgCl2. Let's discuss whose solubility will be greater, NaCl or MgCl2. Now, here, just see the chlorine and chlorine, the chloride and the chloride ions are the common. Just leave it. Now let's focus on the cations. In NaCl, we are having the cation Na positive, and in case of MgCl2, we are having the cation to be Mg2 positive. Now, obviously, the charge of Mg2 positive is greater than Na1 positive, and on the another hand, the radius of Na positive will be greater than the radius of Mg2 positive. So, what will be the charge density? Here, the charge density phi comes out to be the charge to be 1 positive divided by radius of Na positive, and here charge density comes out to be 2 positive divided by radius to be the radius of Mg2 positive, which confirms that charge density of Mg2 positive is very much greater than the Na positive. That means MgCl2 will have higher hydration energy than NaCl, which means that higher hydration energy means higher solubility. MgCl2 will have higher hydration energy as well as higher solubility than the NaCl or the sodium chloride. Now let's take another example. Here I am taking an example group wise. Let's take NaCl and KCl, the sodium chloride and the potassium chloride. Here also we are having the chloride ion to be common, the Cl and the Cl. Then just leave it. Now let's focus on these Na positive and the K positive. Both have charge to be 1 positive, but the radius of Na positive will be smaller than the radius of K positive because K is beneath sodium in group number 1. So the potassium will have the higher radius than that of the sodium, which means that charge density, as it's inversely proportional to radius, the charge density of Na positive will be greater than the charge density of the K positive, which signifies that hydration energy of NaCl will be greater than the hydration energy of KCl, which signifies that solubility of NaCl in water will be greater than the solubility of KCl in water. So that's all about the hydration energy. and the solubility. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.